So here's something worth thinking about as you settle in tonight. Right now, wherever you are, there's probably a clock nearby. Maybe it's on your phone. Maybe it's on the wall. Maybe it's just those little numbers glowing on a microwave across the room. And that clock is ticking away or counting away, dividing your night into hours and minutes and seconds with this quiet, absolute confidence. Like it knows exactly what time it is. Like time is just this obvious, settled thing that humans figured out a long time ago and moved on from. But here's the thing. Time, the measuring of it, the keeping of it, the whole idea of agreeing on what time it actually is right now. That's one of the longest, strangest, most obsessive engineering projects in all of human history. We've been working on it for thousands of years, and honestly, we're still working on it. The clocks you rely on today are the end product of an unbroken chain of invention and failure and wild creativity stretching back to the very first moment some person looked up at the sky and thought, I need to know when. So, let's start there. Let's start with the sky. Because that's where it all begins, right? Long before anyone had built anything, long before gears or pendulums or quartz crystals, there was just the sky. And the sky gives you time for free if you're paying attention. The sun comes up, the sun goes down. That's a day. The moon swells from nothing to full and back again. That's roughly a month. The stars wheel overhead in patterns that repeat, and if you watch them long enough, you start to notice that certain stars appear in certain positions at certain times of year, and eventually the whole pattern resets. That's a year, and this is what people had for a very, very long time. Tens of thousands of years, probably. Celestial time, sky time. You didn't need a device. You just needed to watch. And if you think about it, that's remarkable, because it means the first timekeeping instrument in human history was the human eye paired with human memory. Someone had to notice the pattern, and then someone had to remember it, and then someone had to pass that knowledge on. That's the foundation of everything that comes after. Now, the thing about sky time is that it's actually pretty good for the big stuff. Planting crops, migrating with herds, knowing when the rainy season is coming. For all of that, you just need to know roughly where you are in the year, and the sky tells you. But it's terrible for the small stuff. The sky doesn't tell you how long it's been since noon. It doesn't tell you when to meet someone at the market. It doesn't divide the day into usable pieces. And as soon as people started living in groups, in settlements, in anything resembling a society, they needed the small stuff. They needed to chop the day up. So the first real timekeeping device, the first engineered thing built specifically to measure time, was the sundial. And you probably have a picture in your head of what a sundial looks like. A flat disc with a triangular fin sticking up, casting a shadow. Simple, right? Almost quaint. But here's what's really clever about even the most basic sundial. It's not just telling you where the sun is. It's translating the rotation of the entire Earth into a readable mark on a surface. That shadow is a projection of Earth's angular relationship to the sun at that specific moment, at that specific latitude. That's not trivial. That's actually a beautiful piece of applied astronomy, and people figured it out thousands of years before they had any formal understanding of what the Earth was doing. The oldest known sundials go back to ancient Egypt, around 1500 BCE, though there's evidence that the concept is much older. The Egyptians were obsessed with time in ways that went far beyond the practical. Time was sacred to them. It was woven into their religion, their architecture, their entire cosmology. And they were the first civilization we know of that divided the day into something resembling hours. Not our hours. Their system was different. They split the daylight period into 12 parts and the nighttime into 12 parts, which gives you 24 divisions total. And hey, that number might sound familiar. But here's the catch, and this is a detail that trips people up. Those 12 daytime hours and 12 nighttime hours weren't equal. In summer, when the days were long, each daytime hour was longer than each nighttime hour. In winter, it flipped. The hours themselves stretched and compressed with the seasons. Think about what that means for a second. If you're an Egyptian worker and your boss says, "Be at the construction site at the 3rd hour," the actual duration of time that represents changes depending on what month it is. We call these temporal hours or seasonal hours, and they were the standard way of dividing the day across most of the ancient world for well over 2,000 years. The idea of fixed equal hours, what we'd call equinoctial hours, didn't become the norm until much, much later. We'll get to that. But anyway, sundials. The Egyptians built them, the Babylonians refined them, and then the Greeks took them and ran. The Greeks were extraordinary at this. A man named Anaximander, who lived around 610 to 546 BCE, is often credited with introducing the sundial to Greece, though he probably adapted it from Babylonian models. But what the Greeks did was bring geometry into the picture. They started thinking rigorously about the relationship between the angle of the gnomon, that's the part that casts the shadow, and the latitude of the location. They realized that if you tilt the gnomon so it's parallel to the Earth's axis, the shadow moves at a constant rate, which makes the hour markings evenly spaced. That's a huge insight. That's the difference between a sundial that sort of works and a sundial that's actually precise. And the Greeks built some extraordinary ones. There's a device called the Tower of the Winds in Athens, built around the 1st or 2nd century BCE, which is essentially an octagonal marble tower with sundials on multiple faces, designed so you could read the time from almost any direction. It's still standing, by the way. You can go see it. 2,000 years old, and it's still there. Still telling time when the sun hits it right. But sundials have an obvious problem, and you've probably already thought of it. They don't work at night. They don't work when it's cloudy. They don't work indoors. And if you're trying to coordinate anything that happens after sunset, religious rituals, military watches, any kind of nighttime activity, you need something else. So people invented water clocks. And this is where the engineering starts to get genuinely interesting, because a water clock seems simple, but is actually full of subtle problems that took centuries to solve. The basic idea is about as straightforward as it gets. You have a container of water with a small hole in it. Water drips out at a more or less steady rate. You mark the water level on the side of the container, and as the level drops, it passes the marks, and that tells you how much time has passed. The Greeks called this a clepsydra, which literally means water thief, and that's a lovely name for it. Time is being stolen away, drip by drip. The Egyptians had water clocks too, going back to at least 1400 BCE. There's a beautiful example from the Temple of Amun at Karnak, an alabaster vessel shaped like a truncated cone, with small markings on the inside wall. But here's the engineering problem that plagued every early water clock. The flow rate isn't actually constant. When the container is full, the water pressure at the hole is higher, so water flows out faster. As the level drops, the pressure drops, and the flow slows down, which means your first hour is shorter than your last hour. The clock lies to you, and it lies worse and worse as it runs. Now, The Egyptians partly dealt with this by making the container wider at the top and narrower at the bottom, that truncated cone shape. The idea being that when the water level is high and flowing fast, there's more volume to get through per unit of height, which partially compensates for the faster flow. It's not a perfect solution, but it shows that they understood the problem and were engineering around it. That's impressive for 1400 BCE. But the real breakthrough in water clock design came from a Greek engineer named Ctesibius, who lived in Alexandria around the 3rd century BCE. And Ctesibius is one of those figures in engineering history who deserves to be far more famous than he is. He's sometimes called the father of pneumatics. He invented all sorts of things: a water organ, an improved catapult, various pneumatic devices. But his masterpiece, at least for our purposes, was his improved water clock. Here's what Ctesibius figured out. Instead of trying to compensate for the changing flow rate in the main vessel, he added a second vessel, a regulator. Water flows from a source into this intermediate container, and the intermediate container has an overflow mechanism that keeps the water level in it absolutely constant. Then water drips from this constant level container into the measuring vessel at a truly steady rate. It's a feedback system. The overflow handles the variation, so the output doesn't have to. And that is, when you think about it, one of the earliest examples of a regulated system in engineering history. A constant level reservoir feeding a precision output. You see that same principle in hydraulic systems, in fuel delivery, in all sorts of modern engineering. Ctesibius got there in 250 BCE. His clocks were reportedly accurate to within about 15 minutes over a full day, which might not sound amazing by modern standards. But remember, this is the ancient world. 15 minutes a day was extraordinary, and he added all sorts of elaborate features. A rising float connected to a pointer that indicated the hour on a rotating drum, mechanisms that adjusted for the seasonal hours that everyone still used, even little automated figures that would move as the hours passed. These were machines, real, complex, engineered machines, built to measure something you can't see or touch. And here's a detail I love about Ctesibius. Almost none of his original writings survive. We know about his work primarily through descriptions by other ancient authors: Vitruvius, Philo of Byzantium, Hero of Alexandria. His actual devices are gone, but the ideas persisted. They were copied, refined, transmitted across cultures and centuries. The Romans adopted Greek water clocks. The Islamic world inherited them and made them even more sophisticated. There's a tradition of elaborate water clocks in medieval Islam that's absolutely stunning. Monumental devices with automata, with bells and moving figures, designed not just to tell time, but to display the ingenuity of their makers. One of the most famous is the elephant clock, described by the great engineer Al-Jazari in his 1206 treatise, The Book of Knowledge of Ingenious Mechanical Devices. Al-Jazari was working in what's now southeastern Turkey, and his elephant clock was a masterpiece of multicultural engineering. It incorporated design elements from Greek, Indian, Egyptian, and Chinese traditions, all housed in a decorative elephant figure. Water dripped into a mechanism inside the elephant, triggering a sequence of automata every half hour. A bird would tweet, a man would seem to write, little figures would move. It was a clock, but it was also a performance, a statement about the sophistication of the civilization that produced it. And all of this, the sundials, the water clocks, the automata, all of it was still operating under that ancient assumption of seasonal hours. Hours that changed length with the seasons. Hours that were, in a sense, alive, tied to the actual rhythm of the Earth's relationship with the sun. It wasn't until a very different kind of technology came along that the hour became fixed, became rigid, became the 60-minute block we know today. And that technology emerged from a place you might not expect. It came from the monasteries of medieval Europe, where monks needed to pray at very specific times of day. And the pressure to standardize those times would eventually drive one of the most important inventions in the history of engineering. Because here's the thing about monastic life. It was structured around prayer, and not just prayer in a general sense, but prayer at very particular moments. The Rule of Saint Benedict, written around 530 CE, laid out a daily schedule of 8 canonical hours: matins, lauds, prime, terce, sext, none, vespers, and compline. And these weren't suggestions. They were obligations. The whole spiritual architecture of monastic existence depended on communities of monks gathering together at the right times, day and night, year-round. Matins happened in the deep darkness before dawn. Lauds came at first light. Prime was at roughly 6 in the morning, and so on through the day, every few hours, until compline closed things out in the evening. Now, imagine you're the monk responsible for waking everyone up for matins. It's the middle of the night. There's no clock on the wall. You might have a candle marked with lines, burning down at a roughly predictable rate. You might have a water clock if your monastery was wealthy and sophisticated enough. You might just watch the stars through a window if the sky was clear. But none of these methods were terribly reliable, especially in Northern Europe, where overcast skies could last for weeks. And getting the timing wrong wasn't a minor inconvenience. It was a spiritual failure. You were disrupting the rhythm of devotion that your entire community had organized its life around. So there was real pressure, genuine institutional pressure, to find better ways to mark the passage of time. And this is one of those beautiful moments in engineering history where a very specific practical need, monks need to know when to pray, ends up catalyzing a technological revolution that reshapes the entire world. Because the solution that eventually emerged from this problem was the mechanical clock. And the mechanical clock didn't just change how people told time, it changed what time meant. Let's talk about how that happened. The key innovation, the thing that makes a mechanical clock fundamentally different from everything that came before, is a mechanism called the escapement. And to understand why that matters, think about what a clock actually needs to do. It needs to take some source of energy, falling water, a hanging weight, a coiled spring, and release that energy in controlled, equal, repeatable intervals. That's it. That's the whole game. A water clock does this by letting water flow at a steady rate. But a mechanical clock does something cleverer. It uses a device that repeatedly catches and releases a gear train, letting it advance by exactly one tooth at a time, tick by tick. That catching and releasing, that's the escapement. It's called that because it allows energy to escape from the system in tiny measured doses. The earliest form we know about is called the verge and foliot escapement. And honestly, it's a gorgeous piece of engineering for its time. Picture a vertical shaft, the verge, with 2 small metal plates, called pallets, sticking out from it at roughly right angles to each other. These pallets engage with a toothed wheel called the crown wheel, which is being driven by a weight on a rope wound around a drum. As the crown wheel tries to turn, one pallet catches a tooth and stops it. But the momentum of the system pushes the verge to rotate, which pulls that pallet free and swings the other pallet into the path of a tooth on the opposite side of the crown wheel. And now the tooth pushes back, reversing the rotation of the verge, and the whole cycle repeats. Back and forth, tick and tock. Sitting on top of the verge is the foliot, a horizontal bar with small weights on each end. The foliot's moment of inertia controls how fast the verge oscillates. Move the weights outward, the oscillation slows down, and the clock runs slower. Move them inward, it speeds up. Here's what's really clever about this. It's entirely mechanical. No water, no sand, no burning candles. Just gravity pulling a weight and a mechanism parceling out that gravitational energy into equal little packets. It's a fundamentally different approach to the problem of timekeeping, and it opened up possibilities that water clocks never could. Now, who invented this? That's one of those questions where the honest answer is, we're not entirely sure. The historical record gets murky. There are references to mechanical clocks in European documents starting in the late 1200s. Some historians point to a clock installed at Dunstable Priory in England in 1283 as one of the earliest documented examples. Others cite records from cathedrals in Italy around the same period. The truth is, the verge escapement probably emerged gradually, possibly developed independently in more than one place, refined by craftsmen whose names we'll never know. What we do know is that by the early 1300s, large mechanical clocks were being installed in cathedrals and public buildings across Europe, and they were changing the texture of daily life in ways that are hard to overstate. Think about what a cathedral clock meant to a medieval town. Before that clock existed, time was local and approximate. The church bells rang when someone decided it was time for them to ring. Farmers worked until the light failed. Market hours were loosely defined. But now, suddenly, there was a machine in the center of town that announced the hours with authority. It didn't care about the season. It didn't care whether the sun was up or down. It ticked off equal hours, the same length in January as in July, and everyone within earshot organized their lives around it. And this is the moment, right here, when equal hours start to replace seasonal hours. It didn't happen overnight. People had been living with variable length hours for thousands of years, and old habits die hard. But the mechanical clock made equal hours practical in a way they'd never been before. And once you have a machine that naturally divides the day into 24 identical segments, the old system starts to feel cumbersome. Why would you adjust your hour lengths with the seasons when the clock in the town square is already giving you a perfectly steady rhythm? The technology didn't just measure time differently. It redefined what an hour was. One of the most spectacular early examples is the astronomical clock at Strasbourg Cathedral. The first version was built around 1352 to 1354, and it was astonishing. It didn't just tell the time. It showed the positions of the sun and moon, the phases of the moon, the calendar of saints' days, and it featured elaborate automata, including a rooster that would crow and flap its wings. These cathedral clocks were as much about civic pride and religious devotion as they were about timekeeping. They were statements. Our city has the resources, the knowledge, the craftsmanship to build this extraordinary machine. And the clockmakers who built them were among the most respected artisans in Europe. But here's the thing about those early mechanical clocks. They weren't very accurate. The verge and foliot escapement was a breakthrough, no question, but it had real limitations. The oscillation of the foliot isn't naturally isochronous, meaning the period of each swing isn't perfectly constant. It varies depending on how much force the driving weight is exerting, which changes as the weight descends and the torque on the gear train shifts. A well-maintained tower clock in the 1300s might lose or gain 15 minutes a day. That sounds terrible by modern standards, but remember, it was still better than most water clocks in northern European climates, and it was reliable enough to ring the hours for a town that had previously had no precise timekeeping at all. The real accuracy revolution wouldn't come for another 300 years, and it would hinge on something Galileo Galilei noticed, or at least something he's credited with noticing, around 1583. The story goes that young Galileo, then a medical student at the University of Pisa, was sitting in the cathedral watching a chandelier swing back and forth. Maybe it had been set swinging by a sexton pulling it aside to light it, or maybe by a gust of air. Whatever started it, Galileo noticed something that struck him as remarkable. He timed the swings against his own pulse, because he didn't have a clock handy, which is kind of perfect, and he found that whether the chandelier swung in a wide arc or a narrow one, each swing seemed to take the same amount of time. The amplitude changed, but the period stayed constant. This property is called isochronism, and it's the single most important principle in the history of precision timekeeping. A pendulum of a given length takes the same time to complete each swing regardless of how far it swings. Well, almost. Galileo's observation was approximately true, not perfectly true, and the distinction would matter enormously later. But the core insight was revolutionary. If you could harness a pendulum as the regulating element of a clock, you'd have something far more stable than a foliot, because the pendulum's period is determined almost entirely by its length and the local force of gravity, not by the messy, variable forces in the gear train. Galileo understood this, and late in his life, we're talking the late 1630s, when he was old and going blind, he sketched out designs for a pendulum clock. His son Vincenzo even started building one after Galileo's death in 1642, but he died himself before completing it. So the credit for actually building the first working pendulum clock goes to someone else entirely, a Dutch mathematician and physicist named Christian Huygens. Huygens is one of those figures who deserves to be far more famous than he is. Born in 1629 in The Hague, he was the son of a prominent diplomat and poet, educated by private tutors, brilliant in mathematics from an early age. He corresponded with Descartes. He discovered Titan, the largest moon of Saturn. He proposed a wave theory of light, decades before it became accepted. And in 1656, he designed and had built the first practical pendulum clock. The improvement was dramatic. Where the best verge and foliot clocks might drift 15 minutes a day, Huygens's pendulum clocks could be accurate to within about 15 seconds a day. That's a 60-fold improvement. Think about what that means. Suddenly, you had a device that could reliably track minutes, not just hours. The resolution of human timekeeping jumped by an order of magnitude almost overnight. But Huygens wasn't satisfied. He was a mathematician, and the approximately isochronous nature of the simple pendulum bothered him. A circular pendulum, one swinging along a circular arc, which is what a simple pendulum does, isn't perfectly isochronous. The period does change very slightly with amplitude. For a clock that's supposed to be precise, that tiny variation matters. So Huygens set out to find the curve along which a pendulum would be truly, mathematically, perfectly isochronous, where the period would be absolutely identical regardless of the amplitude of the swing. And he found it. The curve is called a cycloid, the shape traced by a point on the rim of a wheel as it rolls along a flat surface. If you constrain a pendulum to swing along a cycloidal path instead of a circular one, the period becomes exactly constant. Huygens proved this mathematically and then figured out an ingenious way to make it work mechanically. He placed curved metal cheeks on either side of the pendulum's suspension point, shaped as cycloids themselves, so that as the pendulum string rapped against them, during each swing, the bob was forced to follow a cycloidal path. It was a beautiful marriage of pure mathematics and practical engineering. In practice, the cycloidal cheeks introduced their own friction problems and didn't always improve things as much as the theory promised. Later clockmakers found that simply keeping the pendulum's amplitude small, where the circular arc closely approximates a cycloid anyway, was a more practical solution. But the intellectual achievement was enormous. Huygens published his findings in 1673 in a work called Horologium Oscillatorium, which is one of the great masterpieces of 17th century science. It's not just a book about clocks. It contains fundamental contributions to the mathematics of curves, the physics of circular motion, and the concept of centrifugal force. And here's where the story takes a turn that connects timekeeping to one of the most consequential practical problems of the age, a problem that was costing lives and fortunes and driving governments to offer enormous cash prizes for a solution. Because accurate clocks weren't just useful for monks and merchants and astronomers, they were desperately needed by sailors. And the reason has everything to do with a problem that had haunted navigation for centuries, the problem of determining longitude at sea. If you've ever wondered why clockmaking became such an obsession in the 17th and 18th centuries, why kings and parliaments poured money into it, why some of the finest minds in Europe devoted their careers to making clocks just a little bit more precise, this is why. And the story of how that problem was finally solved involves one of the most unlikely heroes in the history of engineering, a self-taught carpenter from the English countryside who would spend the better part of his life fighting not just the technical challenge of building a clock that could keep time on a rolling, pitching, salt-sprayed ship, but also fighting the scientific establishment that refused to believe a man like him could possibly succeed. His name was John Harrison, and his story is one of the most compelling in the entire history of technology. But before we get to Harrison himself, let's make sure you really feel why this problem mattered so much, because it's one of those things that seems abstract until you think it through. And then it hits you just how life and death it really was. So here's the deal with longitude. If you're a sailor out on the open ocean, you need to know two things about where you are: your latitude, which is how far north or south you are, and your longitude, which is how far east or west. Latitude had been solvable for a long time. You could measure the angle of the sun at noon or the angle of the North Star above the horizon at night, and with some tables and a little math, you could figure out your latitude pretty reliably. Sailors had been doing this for centuries. But longitude? Longitude was a nightmare. There's no fixed celestial reference that just hands you your east-west position the way the North Star helps with north-south. And the consequences of not knowing your longitude were catastrophic. You could think you were hundreds of miles from land and sail straight into a reef. You could think you were approaching your destination from one direction when you were actually way off course. Ships were lost. Fleets were lost. Thousands of people drowned. One of the most infamous disasters happened in 1707, when a fleet of British Royal Navy ships under Admiral Sir Cloudesley Shovel was returning home from the Mediterranean. They'd been at sea for weeks, visibility was poor, and they misjudged their position. They thought they were safely west of the Isles of Scilly, off the southwestern tip of England. They weren't. 4 ships struck the rocks. Between 1,400 and 2,000 men died, including Shovel himself. It was one of the worst maritime disasters in British naval history, and the root cause was simple. They didn't know their longitude. Now here's where time comes in, and this is the connection that makes the whole thing click. The Earth rotates 360 degrees every 24 hours. That means it rotates 15 degrees every hour. So if you know what time it is right now where you are, local time, which you can determine by observing the sun, and you also know what time it is right now at some reference location, say London, then the difference between those two times tells you how far east or west you are from London. Every hour of difference equals 15 degrees of longitude. Every minute of time difference equals a quarter of a degree. It's beautifully simple in principle. All you need is a clock set to London time that you can carry with you on the ship, and then you compare it to local noon wherever you are. But here's the thing. The clock has to be accurate. Really, really accurate. At the latitudes where most Atlantic sailing happened, an error of just 1 minute of time could translate to roughly a mile of position error. If your clock drifted by, say, 3 minutes over the course of a long voyage, you could be 3 miles off in your reckoning. That might not sound like much, but pile up errors over weeks or months at sea, and you're looking at the kind of mistake that puts you on the rocks. The general target that emerged was that a useful longitude clock needed to be accurate to within about 3 seconds per day over the course of a voyage that might last several months. 3 seconds per day. Think about what that means compared to where clockmaking was at this point. Huygens's best pendulum clocks, the finest precision instruments in the world, could manage maybe 15 seconds per day on land, in a stable room, on a solid floor. Now, imagine trying to hit 3 seconds per day on a ship that's rolling and pitching, where the temperature swings from tropical heat to North Atlantic cold, where the air is thick with salt spray and humidity, where the whole vessel is vibrating from the waves and the rigging. A pendulum clock was essentially useless at sea. The pendulum needs gravity pulling straight down to work properly, and on a rolling ship, straight down is constantly changing. Huygens actually tried. He built marine pendulum clocks and tested them on voyages in the 1660s. They didn't work well. The motion of the ship threw everything off. So in 1714, the British Parliament passed the Longitude Act, which established the Board of Longitude, and offered a series of prizes, up to £20,000 for a method that could determine longitude at sea to within half a degree. £20,000 in 1714 was an almost unimaginable fortune. It's hard to pin down exact modern equivalents, but we're talking millions, enough to make someone wealthy for life. And the prize was open to anyone. You didn't need to be a fellow of the Royal Society or a professor at Cambridge. You just had to solve the problem. And this is where John Harrison enters the picture. He was born in 1693 in Falby, Yorkshire, the son of a carpenter. He had almost no formal education. He grew up working with wood, learning his father's trade. But he was one of those people who just had an extraordinary mechanical mind, the kind of person who looks at a mechanism and intuitively understands how the parts relate, where the friction lives, what's limiting the precision. By his early 20s, he'd built several long-case clocks, grandfather clocks, essentially, almost entirely out of wood, and they were remarkably good. He'd figured out things independently that established clockmakers hadn't. He invented a type of escapement called the grasshopper escapement that operated with almost no friction and required no lubrication, which was a huge deal because lubricating oils of the era would thicken and gum up over time, degrading a clock's accuracy. He also developed what's called a gridiron pendulum, a pendulum made of alternating rods of brass and steel that expanded and contracted with temperature changes in opposite ways, so the effective length of the pendulum stayed constant regardless of temperature. That's ingenious. He's solving the thermal expansion problem with nothing but a clever arrangement of two different metals. Around 1730, Harrison traveled to London with drawings and plans for a marine timekeeper. He sought out George Graham, one of the most respected clockmakers in England, a fellow of the Royal Society, a man who'd made significant improvements to pendulum clocks and astronomical instruments. And here's one of those lovely moments in the story. Graham was supposed to give Harrison a brief meeting, maybe look at his drawings politely and send him on his way. Instead, they talked for hours. Graham recognized immediately that this self-taught carpenter from Yorkshire was the real thing. He ended up lending Harrison money out of his own pocket to build his first marine clock, with no interest and no fixed repayment date, just one craftsman recognizing brilliance in another. Harrison's first marine timekeeper, now known as H1, took him about 5 years to build. He finished it around 1735. It's a fascinating machine. It doesn't use a pendulum at all. Instead, it uses a pair of linked balance bars connected by springs, designed so that the motion of the ship affects both bars equally, and the errors cancel out. It weighs about 75 pounds. It's a big, intricate, beautiful contraption, and it works. It was tested on a voyage to Lisbon and back in 1736, and while the results weren't precise enough to win the full longitude prize, they were promising enough that the Board of Longitude gave Harrison money to keep going. And this is where the story becomes something almost poignant, because Harrison didn't just build one clock and call it done. He spent the next quarter century of his life building improved versions, each one representing years of painstaking work. H2 came next, finished around 1741. It was never actually tested at sea because Harrison himself wasn't satisfied with it and was already thinking about H3. And H3 consumed him for nearly 19 years. 19 years on a single clock. He kept finding problems, kept refining, kept discovering that the physics of keeping time at sea was even harder than he'd thought. During those years, he invented new mechanisms, including a bimetallic strip for temperature compensation and a caged roller bearing to reduce friction, inventions that would find uses far beyond clockmaking. But H3 never fully satisfied him either. And then something remarkable happened. While working on H3, Harrison had a conceptual breakthrough. He realized that the answer might not be a bigger, more elaborate machine. It might be a smaller one, much smaller. He'd been experimenting with a personal pocket watch made by another craftsman, and he'd noticed that a well-made watch with a fast-beating balance wheel could actually keep surprisingly good time. The high frequency of the balance wheel, it beat 5 times per second, much faster than a pendulum, made it less susceptible to disturbance from the ship's motion. And if you could apply all the tricks he'd learned about temperature compensation and low-friction escapements to a watch-sized mechanism. So Harrison built H4. And H4 is a watch. Not a massive contraption of bars and springs and counterweights. A watch, about 5 inches in diameter, looking for all the world like an oversized pocket watch. It's exquisitely made, with a level of finishing and craftsmanship that still astonishes watchmakers today. He completed it in 1759, when he was 66 years old. He'd been working on the longitude problem for nearly 30 years. H4 was tested on a voyage to Jamaica in 1761. Harrison's son William carried it aboard HMS Deptford. The voyage took 81 days. When they arrived and checked the watch against the known longitude of Kingston, it had lost only 5 seconds. 5 seconds over 81 days. That's an accuracy of about 1 second per day, far exceeding the requirements of the Longitude Act. It was, by any reasonable standard, a triumph. But here's where the story turns bitter, because the Board of Longitude didn't simply hand over the prize, and the reasons were tangled up in politics, institutional pride, and one particular rivalry that would shadow Harrison's achievement for years. The Astronomer Royal, a man named Neville Maskelyne, was a champion of the competing lunar distance method for finding longitude, an astronomical approach that involved measuring the angle between the moon and certain stars and then doing elaborate calculations. Maskelyne sat on the Board of Longitude, and he had both professional and personal reasons for not wanting a mechanical solution to win. The board kept moving the goalposts. They demanded more trials. They demanded that Harrison explain every detail of H4's construction so that other watchmakers could replicate it, effectively asking him to give away his life's work. They paid him partial sums, but withheld the full prize for years. Harrison was in his 70s by now, and he was furious. He'd devoted his entire adult life to this problem. He'd solved it beyond any reasonable doubt, and the establishment was denying him his due. Eventually, he appealed directly to King George III, who took a personal interest and had H5, Harrison's final timepiece, tested at his private observatory. The king was reportedly outraged by how Harrison had been treated. Under royal pressure, Parliament finally awarded Harrison the bulk of the remaining prize money in 1773. He was 80 years old. He died 3 years later, in 1776. It's a story that has everything: genius, perseverance, institutional obstruction, the collision between practical craft and academic science. And the engineering legacy is immense. Harrison didn't just solve the longitude problem. He advanced the entire field of precision mechanics. His temperature compensation techniques, his low-friction escapements, his understanding of how materials behave under changing conditions, all of this fed directly into the next generation of chronometers and, eventually, into precision engineering more broadly. And the impact on the world was immediate and profound. Within a few decades of Harrison's work, marine chronometers based on his principles became standard equipment on naval and merchant vessels. The oceans became navigable with a confidence that had never existed before. Trade routes became more efficient, voyages became safer, and the maps of the world filled in with an accuracy that previous generations couldn't have imagined. But here's what's really interesting to think about as you're lying there, maybe starting to drift a little. The longitude story shows you something fundamental about the relationship between timekeeping and civilization. Every leap in the accuracy of clocks opened up possibilities that went far beyond just knowing what time it was. Pendulum clocks didn't just tell better time, they enabled the scientific revolution, giving astronomers and physicists a way to measure phenomena precisely. Marine chronometers didn't just keep time at sea, they enabled global navigation and reshaped the political and economic geography of the world. And that pattern was about to repeat itself, because even as Harrison's chronometers were transforming navigation, a completely different pressure was building that would demand yet another revolution in how humanity organized time. Not more accurate clocks this time, but something arguably even more radical: the standardization of time itself across vast distances. And the force that would drive that change was something no one in Harrison's era could have predicted. A machine that turned heat into motion, that consumed coal and breathed steam and pulled things, people, goods, raw materials, across distances at speeds that would have seemed like witchcraft just a generation earlier. The railroad. And the railroad didn't just change transportation. It broke time itself. Or rather, it revealed something about time that had never mattered before, something that no one had ever needed to care about. And to understand why, you need to think about what time actually meant to an ordinary person living in, say, 1830. Because it meant something completely different from what it means to you right now. If you lived in a small English town in the early 19th century, your sense of time was local, completely, utterly local. The clock on the church tower was set by the sun, specifically by solar noon, the moment when the sun reached its highest point in the sky. And that was your town's time. That was the time. If you walked 10 miles west to the next town, their church clock would read slightly differently, because the sun reaches its highest point a little later the farther west you go. The difference was small, roughly 4 minutes for every degree of longitude, which works out to maybe a minute or two between neighboring towns. And nobody cared. Why would you? You weren't synchronized with the next town. You didn't need to be. You walked there, or you rode a horse, and the journey took hours, and when you arrived, you just looked at their clock and adjusted. Time was a local phenomenon, like weather. Bristol's clocks ran about 10 minutes behind London's. Plymouth was about 16 minutes behind, and that was perfectly fine, because nothing in daily life required those two cities to agree on what time it was. Now think about what happens when you build a railroad between them. Suddenly you have a machine that covers the distance between Bristol and London in a couple of hours instead of a couple of days. Suddenly you need a timetable, a printed schedule that tells people in Bristol when the train leaves and tells people in London when it arrives. And here's the problem. Whose time do you print on the timetable? If you use London time for the London departure and Bristol time for the Bristol departure, your passengers are going to be confused because a journey that takes 2 hours by the clock in London looks like it takes an hour and 50 minutes by the clocks in Bristol. And if someone in Bath is trying to catch a connecting train, which clock are they supposed to trust? Their own? London's? Bristol's? It sounds almost comical, right? But it was a genuine operational nightmare. And it wasn't just confusing for passengers, it was dangerous. Because trains run on tracks, and tracks are shared. And if two trains are heading toward each other on the same line, and the station masters at either end are operating on clocks that disagree by 10 or 15 minutes, you have a recipe for disaster. And disasters did happen. The details of specific early rail collisions are sometimes murky in the historical record, but the problem was well understood by railway operators almost from the beginning. You simply could not run a safe, efficient railroad network when every station kept its own local solar time. So the railroads did something radical. They standardized. The Great Western Railway, which ran that Bristol to London route, was one of the first to adopt what became known as railway time, a single uniform time used across the entire network, regardless of local solar noon. And the time they chose was London time. Greenwich time, specifically, since the Royal Observatory at Greenwich had long been the reference point for British navigation and astronomy. By 1840, the Great Western Railway was running entirely on Greenwich Mean Time. Other railways followed. And gradually, reluctantly, the towns along the routes started to adjust their own clocks to match. But here's what's fascinating. Not everyone was happy about it. Not by a long shot. There was genuine resistance. And when you think about it, you can understand why. Time had always been local. It was tied to the sun, to the rhythms of the actual physical world around you. Telling people in Bristol that their noon wasn't really noon anymore, that they had to set their clocks to match a city 100 miles away, that felt arbitrary. It felt like an imposition. The city of Exeter reportedly held out against railway time for years. There's a famous clock on the facade of a building in Bristol. Some accounts say it was the corn exchange that had 2-minute hands, one showing local time and one showing Greenwich time. A quiet act of protest, or at least of dual acknowledgement. We'll keep your time, the clock seemed to say, but we won't forget our own. Eventually, though, practicality won. It always does with infrastructure. In 1880, the Statutes Definition of Time Act made Greenwich Mean Time the legal time for all of Great Britain. And just like that, an entire country was synchronized. One time, one standard, not because the sun demanded it, but because the trains did. And this same drama played out on an even grander scale across the Atlantic, in the United States and Canada, where the distances were enormous and the problem was correspondingly worse. Think about it. The continental United States spans roughly 60 degrees of longitude. That's a 4-hour difference in solar time between the East Coast and the West Coast. And by the 1870s, the American railroad network was growing explosively, with dozens of different railroad companies, each keeping their own version of time. Some used the local time of their headquarters city. Some used the time of their eastern terminus. Some used Washington time. The result was chaos. There were reportedly more than 300 different local times in use across the United States. A traveler going from Maine to California might have to reset their watch 20 or 30 times. Major rail junctions where multiple lines converged had to maintain clocks showing half a dozen different times simultaneously. The person who finally untangled this mess, or at least one of the key figures, was a Canadian railway engineer named Sanford Fleming. And Fleming's story is worth pausing on, because it illustrates how one person's frustration with a practical problem can reshape the entire world. Fleming was the chief engineer of the Canadian Pacific Railway, and he'd personally experienced the confusion of uncoordinated time. There's a well-known story, and like many well-known stories, the details vary in different tellings, that Fleming missed a train in Ireland in 1876 because a printed schedule listed a time as PM when it should have been AM, or something to that effect. Whether that specific incident happened exactly that way or not, Fleming became passionate about the idea of a rational, worldwide system of timekeeping. His proposal was elegant. Divide the Earth into 24 zones, each 15 degrees of longitude wide, 15 degrees being exactly the amount the Earth rotates in 1 hour. Each zone would keep a uniform time, exactly 1 hour different from its neighbors, and the whole system would be anchored to a single prime meridian. Fleming advocated for this idea tirelessly through the late 1870s and early 1880s, presenting papers, lobbying governments, building international support. The climax came in October 1884 at the International Meridian Conference in Washington, D.C. Delegates from 25 nations gathered to settle 2 questions. Where should the prime meridian be, and should the world adopt a system of standard time zones? The debate was political as much as it was technical. France, naturally, wanted the prime meridian to run through Paris. Several nations proposed a neutral meridian running through the Azores, or through the Bering Strait, or through some other location not associated with any major power. But the practical reality was overwhelming. Roughly 70% of the world's shipping already used charts based on the Greenwich Meridian, thanks to Britain's naval dominance and the long legacy of the Royal Observatory. Greenwich won, with 22 votes in favor, 1 against, that was San Domingo, now the Dominican Republic, and 2 abstentions, France and Brazil. France, in a wonderful bit of diplomatic stubbornness, didn't officially adopt Greenwich Mean Time until 1911, and even then they defined it as Paris Mean Time, retarded by 9 minutes and 21 seconds, which is technically the same thing, but lets you save face. So by the end of the 19th century, the world had something it had never had before: a shared temporal framework, time zones, a prime meridian. The idea that when it's noon in London, it's 7 in the morning in New York and 8 in the evening in Beijing. We take this so completely for granted now that it's hard to appreciate how revolutionary it was. For all of human history up to that point, time had been local, personal, tied to the sun overhead, and then, in the span of about 50 years, driven by the practical demands of railroad scheduling, it became global, standardized, and abstract. Noon stopped meaning the sun is at its highest. It started meaning the clock says 12. And those two things, in most places, are close, but not exactly the same. And here's what's quietly profound about that shift. The standardization of time wasn't really about clocks at all. It was about coordination. It was about the realization that as human systems grow larger and more interconnected, as trains link cities, as telegraphs link continents, as commerce becomes global, everyone needs to agree on a shared framework, even if that framework is, in some sense, a fiction. Solar noon in the western edge of a time zone might be 30 minutes off from what the clock says, but everyone agrees on what the clock says, and that agreement is what makes the system work. It's one of those cases where an approximate convention that everyone shares is infinitely more useful than a precise measurement that's different for every location. The telegraph, by the way, was crucial to making all of this work, and it's easy to overlook. You can decree that every clock in the country should show Greenwich time, but how do you actually synchronize them? Before the telegraph, you couldn't. Not really. You'd have to physically carry a chronometer from Greenwich to each town, and by the time you arrived, you'd have accumulated small errors. But with the telegraph, you could send a time signal, an electrical pulse, from Greenwich to every connected station essentially instantaneously. The Royal Observatory began transmitting time signals by telegraph in 1852, and this became the backbone of British time distribution. In the United States, the Naval Observatory in Washington performed a similar function. Every day, at a precise moment, a signal went out, and clocks across the network were corrected. It was the first time in history that distant clocks could be truly synchronized, and it was electromagnetic technology that made it possible. So think about where we are now in this story. We started with shadows on the ground and water dripping through holes. We moved to mechanical gears and swinging pendulums. We crossed oceans with spring-driven chronometers, and now we've wrapped the entire planet in a web of synchronized, standardized time, distributed at the speed of electricity. Each step was driven not by some abstract desire for better clocks, but by a concrete human need to pray at the right hour, to navigate the seas, to run the trains on time. And each step changed civilization in ways that went far beyond the original problem. But the story doesn't stop here, because the 20th century was about to bring pressures that would make railroad scheduling look simple. The world was about to need time measured not in seconds, but in fractions of seconds, millionths, billionths, trillionths. And the pendulum clock, as beautiful and refined as it had become, was approaching the absolute limit of what a mechanical device could achieve. The next revolution would come not from gears or springs or gravity, but from something almost unimaginably small, something vibrating inside a crystal, and then, later still, something vibrating inside an atom. And the person who first glimpsed that possibility was working in a laboratory that smelled of solder and hot vacuum tubes sometime around 1927. His name was Warren Marrison, and he was a Canadian-born engineer working at Bell Telephone Laboratories in New York. Now, Marison wasn't trying to revolutionize timekeeping. That's one of those beautiful ironies in the history of technology. The people who change everything are often just trying to solve a much smaller, more practical problem. In Marison's case, he was working on frequency standards for telecommunications. Bell Labs needed extremely stable frequencies to keep telephone signals clean and reliable, and Marison had been experimenting with quartz crystals because of a peculiar property they possess, something called piezoelectricity. Piezoelectricity is one of those things that sounds complicated, but is actually pretty intuitive once you think about it. Certain crystals, quartz being the most common, have a molecular structure that responds to mechanical stress by generating a tiny electric voltage. You squeeze the crystal, and it produces a little spark of electricity. But here's the really interesting part. It works in reverse too. If you apply an electric voltage to the crystal, it physically deforms. It flexes, and if you set up the circuit just right, you can get the crystal to vibrate at an extremely consistent frequency. It rings, almost like a tiny tuning fork, except this tuning fork vibrates tens of thousands of times per second, and it does so with a regularity that makes even the best pendulum clock look sloppy by comparison. Marison realized that if you could count those vibrations, and by 1927, electronic circuits were just barely capable of doing this, you could use them as the basis for a clock. Each vibration is a tick. Count enough of them, and you've measured a second. The first quartz clock he built was enormous, nothing like what you'd picture. It filled a room with racks of vacuum tube electronics needed just to sustain the crystal's oscillation and divide down that rapid vibration into something slow enough to drive a clock display. But it worked, and it was accurate to within a few thousandths of a second per day, which was staggeringly better than anything mechanical. Now, to put that in perspective, think about Harrison's H4. That masterpiece of mechanical watchmaking, the culmination of decades of obsessive craftsmanship, could keep time to within about a second a day under ideal conditions. And that was considered miraculous. Marison's quartz clock was roughly 1,000 times more accurate. Not because Marison was 1,000 times more clever than Harrison. He wasn't, and he'd have been the first to say so. But because he was working with a fundamentally different phenomenon. Instead of relying on the mechanical swing of a balance wheel or pendulum, where friction and temperature and air resistance are constantly nibbling away at accuracy, he was relying on the vibration of atoms locked in a crystal lattice. The regularity came from the laws of physics at a molecular level, and that's just a much more stable foundation to build on. For a couple of decades, quartz clocks remained laboratory instruments. They were too big, too expensive, and too power-hungry for everyday use. But they transformed scientific timekeeping almost immediately. Observatories adopted them. They were used to calibrate radio transmissions, and they revealed something that no one had expected. The Earth itself was not a reliable timekeeper. See, up until quartz clocks came along, the second was defined as a fraction of the mean solar day. One day was 24 hours, 1 hour was 60 minutes, 1 minute was 60 seconds, so a second was 1/86,400th of a day. Simple enough. But when scientists started comparing quartz clocks against the rotation of the Earth, they discovered that the Earth's rotation isn't constant. It wobbles. It speeds up and slows down by tiny amounts due to tidal forces, shifts in atmospheric circulation, even the redistribution of mass from melting ice caps. The variations are minuscule, milliseconds here and there, but quartz clocks were precise enough to detect them. Think about what that means. For thousands of years, the spinning Earth was the ultimate clock. Every timekeeping device humans ever built was calibrated against it. Sundials measured the Earth's rotation directly. pendulum clocks were set by astronomical observations. Harrison's chronometers were tested against the stars. And now, suddenly, the student had surpassed the teacher. The clocks were more regular than the planet. That's a genuinely profound moment in the history of timekeeping, and it happened so quietly that most people never noticed. But quartz was really just the warm-up act. The true revolution was already brewing, and it came from an idea that had been floating around in physics since the late 1930s. In 1945, a Columbia University physicist named Isidore Isaac Rabi gave a lecture. And Rabi was a fascinating character, a Nobel laureate who'd won the prize in 1944 for his work on magnetic resonance. He was born in what's now Poland, grew up in New York City, and had this wonderful combination of deep theoretical insight and practical imagination. In his lecture, Rabi suggested that the natural resonance frequencies of atoms could be used as the basis for a clock of unprecedented accuracy. Here's the idea, and it's worth slowing down for, because it's genuinely beautiful. Every atom of a given element vibrates at exactly the same frequency. Not approximately the same, exactly. Every cesium-133 atom in the universe, whether it's sitting in a laboratory in London or drifting through interstellar space, has the same resonant frequency. This is a consequence of quantum mechanics, and it's one of the most remarkable facts about the physical world. Unlike a pendulum, which can be lengthened or shortened, or a quartz crystal, which can be cut to slightly different thicknesses, an atom's frequency is fixed by the fundamental constants of nature. You can't adjust it. You can't wear it out. It just is. So if you could build a device that locked onto that frequency, that listened, in effect, to the vibration of atoms and counted the oscillations, you'd have a clock that was accurate not because of clever engineering, but because of the unchanging laws of physics themselves. The engineering challenge was figuring out how to actually do it. The first person to build a working atomic clock was Harold Lyons at the National Bureau of Standards in Washington, D.C. in 1949. His clock used ammonia molecules, and honestly, it wasn't much more accurate than the best quartz clocks of the time. It was more of a proof of concept, a demonstration that yes, you could lock an oscillator to an atomic resonance and use it to keep time. The real breakthrough came a few years later, in 1955, at the National Physical Laboratory in Teddington, England. And the engineer who made it happen was Louis Essen. Essen is one of those figures who deserves to be far more famous than he is. He was a meticulous, somewhat stubborn English physicist who had spent years working on precision measurements of the speed of light. He understood frequency and oscillation at a deep level, and when he turned his attention to atomic clocks, he chose cesium as his element. There were good reasons for this. Cesium-133 has a hyperfine transition, a specific quantum mechanical flip in the orientation of its outermost electron spin relative to the nucleus that produces microwave radiation at a very precise frequency. 9,192,631,770 cycles per second. That number might sound arbitrary, but it's as fixed and universal as the speed of light itself. Essen, working with Jack Perry, built a cesium beam clock that was accurate to about 1 second in 300 years, and within a decade, improved versions were accurate to 1 second in thousands of years. This was so much better than anything that had come before that it forced a fundamental redefinition. In 1967, the 13th General Conference on Weights and Measures made a decision that would have astonished every astronomer and clockmaker in history. They redefined the second. No longer was it a fraction of the Earth's rotation or its orbit around the Sun. The second was now defined as exactly 9 192,631,770 periods of the radiation, corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Time was no longer tied to the heavens. It was tied to the atom. And that redefinition wasn't just academic housekeeping. It had immediate, practical consequences that ripple through your life right now, tonight, even as you're lying here listening to this. Because once you have clocks that accurate, you can do things that were previously impossible. You can measure the speed of light with enough precision to redefine the meter itself, which is exactly what happened in 1983. You can build navigation systems that depend on knowing the time to within billionths of a second. And that brings us to something you've almost certainly used today, probably without thinking about it even once. The Global Positioning System, GPS, is, at its heart, a timekeeping system. Each GPS satellite carries multiple atomic clocks, and your position is determined by measuring the tiny differences in the time it takes signals from different satellites to reach your phone. Light travels about 30 centimeters, roughly a foot, in 1 nanosecond, 1/1000th of a second. So if your phone's calculation of the signal travel time is off by even 100 nanoseconds, your position is off by about 30 meters. That's the difference between the GPS showing you on the right street and showing you in the middle of a river. The whole system works only because those satellite clocks are accurate to within a few nanoseconds per day, and they're continuously corrected by ground stations running even more precise atomic clocks. But here's something about GPS that most people don't know, and it connects to physics in a way that would have delighted Einstein. The atomic clocks on GPS satellites actually tick at a slightly different rate than identical clocks on the ground. There are two effects at work. First, the satellites are moving at about 14,000 kilometers per hour relative to the Earth's surface, and special relativity tells us that moving clocks run slow. This effect makes the satellite clocks lose about 7 microseconds per day compared to ground clocks. But second, the satellites are about 20,000 kilometers above the Earth, where gravity is weaker, and general relativity tells us that clocks in weaker gravity run faster. This effect adds about 45 microseconds per day. The net result is that the satellite clocks gain roughly 38 microseconds per day relative to ground clocks. If this relativistic correction weren't programmed into the system, GPS positions would drift by about 10 kilometers per day. Within a week, the system would be useless. So every time you open a map on your phone, you're relying on atomic clocks precise enough to reveal the curvature of space-time predicted by Einstein in 1915. You're relying on corrections derived from both special and general relativity. And you're relying on a definition of the second that was anchored to cesium atoms in a laboratory in Teddington, England, by a meticulous physicist named Louis Essen, who just wanted to measure things properly. The layers of history and physics folded into that one casual gesture, glancing at your phone to see where you are extraordinary when you stop to think about them. But even cesium clocks, as astonishing as they are, weren't the end of the story. Because by the late 20th century, physicists were already pushing towards something even more precise, using not microwaves, but visible light, and not beams of atoms, but single trapped ions held almost perfectly still in electromagnetic cages cooled to temperatures just barely above absolute zero. These are called optical clocks, and the accuracy they're achieving is almost hard to believe. We're talking about clocks that would neither gain nor lose a single second in roughly 15 billion years. That's longer than the current age of the universe. Let that sit with you for a moment. A clock so stable that if you had started it ticking at the Big Bang, it would still be accurate today, and the way they achieve this is genuinely beautiful. So let me walk you through it, because it builds on everything we've been talking about, from Huygens counting pendulum swings to Essen counting microwave cycles. The basic idea is the same one Isidore Rabi dreamed about back in 1945. You use the natural resonance of an atom as your frequency standard. But instead of using microwave transitions in cesium, optical clocks use transitions in atoms like strontium or aluminum or ytterbium that oscillate at the frequencies of visible light. And here's why that matters. Remember how the cesium standard works. The atom oscillates at about 9.2 billion cycles per second. That's fast. But visible light oscillates at frequencies hundreds of thousands of times higher, around hundreds of trillions of cycles per second. Think of it this way. If you're trying to measure the length of something, and you have two rulers, one marked in centimeters and one marked in micrometers, the micrometer ruler gives you a much finer measurement. Same principle here. The higher the frequency of your atomic oscillation, the finer you can slice time, and the more precisely you can define each tick. But working at optical frequencies is enormously harder than working at microwave frequencies. For decades, there was no practical way to count oscillations that fast. You could generate them, you could detect them, but you couldn't actually count them with enough precision to use them as a clock. That changed in the late 1990s and early 2000s thanks to a tool called the optical frequency comb. And the story behind it is one of those wonderful cases where work in one area of physics unexpectedly handed the keys to an entirely different problem. The frequency comb was developed primarily by two physicists, John Hall at GILA in Boulder, Colorado, and Theodor Hensch at the Max Planck Institute in Garching, Germany. They shared half of the 2005 Nobel Prize in Physics for this work. What a frequency comb does is essentially create a bridge between microwave frequencies, which we can count reliably, and optical frequencies, which are too fast to count directly. Imagine a piano keyboard, but instead of 88 keys, it has hundreds of thousands, and each key corresponds to a precise, evenly spaced frequency of light. A frequency comb generates a spectrum of laser light with these perfectly regular teeth, like the teeth of a comb, hence the name, spanning from microwave frequencies all the way up to optical frequencies. By comparing the optical frequency of your atom's transition to the known spacing of the comb's teeth, you can effectively count those hundreds of trillions per second oscillations. It's an extraordinary piece of physics and engineering, and it turned optical clocks from a theoretical dream into a practical possibility. Now, there's another challenge, and it's one that connects back to something fundamental about temperature and motion. If your atoms are moving around, bouncing, jittering, flying through a beam, their motion shifts the frequency you measure through the Doppler effect. Same thing that makes an ambulance siren sound higher as it approaches you and lower as it moves away. If your strontium atoms are zipping around at room temperature, their thermal motion smears out the frequency you're trying to measure, blurring your tick. So to build the most precise optical clocks, you need to hold your atoms almost perfectly still. This is where laser cooling comes in, and it's one of the most counterintuitive techniques in all of physics. You can actually use laser light to slow atoms down, to cool them. The basic idea, developed through the 1980s and 1990s by physicists like Stephen Chu, Claude Cohen-Tanuji, and William Phillips, who shared the 1997 Nobel Prize for this work, is that if you aim laser beams at atoms from multiple directions, tuned to just the right frequency, the atoms preferentially absorb photons when they're moving toward the laser, and each absorption gives them a tiny kick backward, slowing them down. It's like running into a headwind made of light. You can cool atoms this way to temperatures of just millionths of a degree above absolute zero. At those temperatures, the atoms are barely moving at all. Their Doppler shifts become negligible, and you can hold them there, suspended in electromagnetic traps, sometimes a single ion, one solitary atom floating in a vacuum, pulsing at its natural frequency with almost unimaginable regularity. One of the leading optical clocks in the world right now uses a single aluminum ion, trapped and cooled, with its quantum state read out through a companion magnesium ion in the same trap. This clock, developed at the National Institute of Standards and Technology, NIST, in Boulder, Colorado, has demonstrated accuracy at the level of about 1 second in 30 billion years. Another approach, also at NIST and at labs in Tokyo, Paris, and elsewhere, uses lattices of strontium atoms, thousands of them held in a grid made of intersecting laser beams, a structure called an optical lattice. The lattice approach averages over many atoms simultaneously, which reduces statistical noise, and strontium lattice clocks have achieved similar or even better performance. Jun Ye's group at Gila has been at the forefront of this, pushing strontium lattice clocks to precisions that are genuinely staggering. And here's where things get philosophically interesting, because these clocks are so precise that they can actually detect the difference in the flow of time caused by a change in height of just a few centimeters. You heard that right. General relativity tells us that time runs faster at higher altitudes, where gravity is slightly weaker. With GPS satellites, this effect amounts to microseconds per day, because the altitude difference is 20,000 kilometers. But optical clocks are so sensitive that they can measure this gravitational time dilation over the height of a single step on a staircase. Jun Ye's group demonstrated this in 2021. They compared two strontium clocks separated by about a millimeter in height and detected the relativistic difference. Time itself flowing at a measurably different rate across the width of a pencil. This isn't just a party trick. It has profound practical implications. One application is something called relativistic geodesy, using clocks to measure the shape of Earth's gravitational field with extraordinary precision. Because if you place two optical clocks at different locations and compare their tick rates, the difference tells you about the gravitational potential at each point, which in turn tells you about the distribution of mass beneath the surface. You could use networks of optical clocks to monitor changes in underground water tables, to detect magma movement beneath volcanoes, to measure how ice sheets are redistributing mass as they melt. Timekeeping becomes a tool for sensing the planet itself, and it raises a question that the international metrology community has been actively working on for years now. Should we redefine the second again? The cesium definition from 1967 has served beautifully for over half a century. But optical clocks are now so much more precise than the best cesium clocks that the cesium standard is actually the limiting factor. It's like having a ruler that can measure to the micrometer, but the official definition of the meter is only accurate to the millimeter. The tool has outgrown the standard. As of the early 2000s, the international bodies responsible for this, the Bureau International des Poids et Mesures and Sèvres, France, and the various national metrology institutes, have been laying the groundwork for a redefinition. The leading candidates are optical transitions in strontium, ytterbium, and aluminum. The exact timeline is still being worked out, but it seems likely that within the next decade or so, the second will be redefined in terms of an optical frequency, and the cesium era will come to an end. Not because cesium failed, it succeeded magnificently, but because we learned to do better. There's something poignant about that, actually. Every standard in the history of timekeeping has eventually been superseded. The sundial gave way to the water clock. The water clock gave way to the mechanical escapement. The pendulum gave way to quartz. Quartz gave way to cesium. And now cesium is giving way to optical transitions. Each time, the old standard didn't become wrong. It just became insufficiently precise for the questions we were trying to answer. The questions keep getting sharper, and the tools have to keep up. And this progression reveals something else, something deeper about the relationship between timekeeping and our understanding of the universe. Because at every step, more precise clocks didn't just measure time better. They revealed new physics. Pendulum clocks revealed that Earth's gravity varies with latitude. Quartz clocks revealed that Earth's rotation is irregular. Cesium clocks made GPS possible and confirmed relativistic time dilation in everyday technology. And now optical clocks are turning time itself into a probe for gravitational fields, for fundamental constants, for the very structure of space-time. Which brings us to a question that physicists are genuinely grappling with right now, one that takes us to the very edge of what we understand. Because as our clocks have gotten more precise, we've started bumping up against a boundary, a place where our two greatest theories of physics, quantum mechanics and general relativity, don't quite agree on what time even is. And the experiments being designed to explore this boundary are some of the most ambitious in the history of science, and they hinge on clocks, on the very instruments we've been following through this entire story. So let's talk about this tension, because it's genuinely one of the most fascinating puzzles in all of physics, and it turns out that time is right at the heart of it. In general relativity, Einstein's theory of gravity, time is flexible. We've already talked about this. Clocks run slower in stronger gravitational fields. Time is woven into the fabric of space-time, and that fabric can stretch, curve, warp. Time isn't a backdrop against which things happen. It's part of the thing that's happening. It responds to mass and energy. It's dynamic. And we've confirmed this over and over, from GPS corrections to those beautiful experiments where optical clocks at different heights tick at measurably different rates. Now, in quantum mechanics, the theory that governs atoms, particles, the very small, time plays a completely different role. In quantum mechanics, time is a parameter. It's like a fixed stage on which the quantum drama unfolds. Particles evolve according to the Schrödinger equation, and that equation has a little t in it, and that t just ticks along, steady, uniform, unaffected by anything the particles are doing. Time in quantum mechanics is absolute. It's Newtonian almost. It's the one thing in the theory that isn't quantized, isn't uncertain, isn't subject to superposition. Everything else in quantum mechanics can be in two states at once. A particle can be here and there, spinning up and spinning down. But time? Time just marches forward, the same for everyone. You see the problem. In one theory, time bends. In the other, it doesn't. And both theories are spectacularly successful in their own domains. General relativity describes the large-scale structure of the universe with extraordinary precision. Quantum mechanics describes the behavior of atoms and particles with extraordinary precision. But when you try to build a single theory that combines both, a theory of quantum gravity, time becomes the sticking point. Nobody quite knows what to do with it. This isn't just a philosophical curiosity. It's a real, concrete obstacle. Physicists have been trying to unify these two theories for the better part of a century, and the nature of time is one of the deepest barriers. Some approaches, like loop quantum gravity, suggest that time itself might be quantized, that there might be a smallest possible unit of time, a kind of temporal atom below which the concept of duration simply doesn't apply. Others, like certain interpretations of the Wheeler-DeWitt equation, which is one of the key equations in quantum cosmology, seem to suggest that time doesn't exist at all at the fundamental level, that the universe, described in its most basic terms, is static, timeless, and that what we experience as the flow of time is somehow emergent, something that arises from the arrangement of quantum states rather than being built into the foundations. Now that's a head-spinning idea, and you might be thinking, okay, but this is all very abstract. What does it have to do with actual clocks, with actual experiments? And here's where it gets really exciting, because the precision of modern optical clocks is approaching the point where we might actually be able to test some of these ideas. Think about what an optical clock does. It counts oscillations of light interacting with atoms that are quantum mechanical objects sitting in a gravitational field described by general relativity. An optical clock is, in a very real sense, a device that lives at the intersection of both theories. And as these clocks get more precise, they become sensitive to effects that neither theory alone can fully describe. One of the experiments people are seriously discussing involves putting optical clocks into superposition. Now, superposition is that quintessentially quantum phenomenon where a particle can be in two states at once. Normally, we think of superposition applying to tiny things, electrons, photons, individual atoms. But what if you could put a clock, a physical, ticking clock, into a superposition of two different gravitational potentials? What if you could have a single clock that is, in some quantum sense, simultaneously at two different heights, where general relativity says time should flow at two different rates? What would that clock read? Would it tick at both rates at once? Would the two versions of the clock decohere, lose their quantum coherence, because of the time difference between them? This isn't science fiction. Researchers like Igor Pikovsky and his collaborators published a paper in 2015 suggesting that gravitational time dilation could be a source of quantum decoherence, that gravity might actually destroy quantum superpositions precisely because time runs differently at different heights. The idea is that if you have a composite quantum system, like a large molecule, and you put it in a superposition of being at two different heights, the internal dynamics of that molecule, its vibrations, its internal clocks, essentially, would evolve at slightly different rates along the two paths. And that difference, that tiny mismatch in internal time, would cause the quantum interference between the two paths to wash out. Gravity would effectively be measuring which path the molecule took, not by exerting a force, but by creating a time difference. And here's the thing. This is potentially testable. Not easily, not yet, but the precision of modern clocks and atom interferometers is creeping toward the regime where these effects might be observable. Groups around the world are working on experiments to test exactly this kind of thing. There's a proposed experiment called MIGA in France, a matter wave interferometer that would use atom interferometry in a long underground tunnel to search for gravitational effects on quantum coherence. There are proposals to fly optical clocks on the International Space Station, where the combination of microgravity and orbital velocity creates a different relativistic environment. And then there's the question of whether time itself has a minimum resolution, a Planck time, if you will. The Planck time is incredibly small, about 5.4 times 10 to the negative 44 seconds. That's so short that light, traveling at 300 million meters per second, would only cross a distance of about 10 to the negative 35 meters in one Planck time. That distance is called the Planck length, and it's roughly 20 orders of magnitude smaller than a proton. At these scales, our current theories break down entirely. Space-time itself might become foamy, turbulent, quantized. And some physicists have speculated that this quantum foam might leave subtle signatures, tiny fluctuations in the speed of light, for instance, or minute irregularities in the timing of signals from distant astronomical events. Gamma-ray telescopes like the Fermi Space Telescope have actually looked for this. When a gamma-ray burst happens billions of light-years away, photons of different energies travel across the universe to reach us. If space-time has a granular structure at the Planck scale, higher energy photons might travel at very slightly different speeds than lower energy ones, and over billions of light-years, that tiny difference would add up to a measurable time delay. So far, no such delay has been convincingly detected, which actually puts constraints on certain models of quantum gravity. But the search continues, and it's fundamentally a search about the nature of time at the smallest scales. So you see how the story keeps folding back on itself. We started with humans watching the sun cross the sky, trying to organize their days. We moved to water clocks and mechanical escapements, to pendulums and quartz crystals, to atoms vibrating billions of times per second. And now, the very instruments we built to measure time are becoming tools to investigate what time fundamentally is. The clock has gone from being a practical device, wake up, go to work, navigate your ship, to being a scientific instrument that probes the deepest structure of reality. And it's worth pausing here to appreciate something about the people involved in this work, because the community of physicists working on these questions is remarkable. Jun Ye at Gila, whom we mentioned earlier with the strontium lattice clocks, isn't just trying to build a better clock for the sake of precision. He's explicitly motivated by the idea that clocks can become tools for fundamental physics. In interviews, he talks about using clocks to search for dark matter, the mysterious substance that makes up about 27% of the universe's mass energy, but has never been directly detected. Some theoretical models suggest that dark matter could cause tiny transient fluctuations in the fundamental constants of nature, and if you had a network of optical clocks spread across the Earth, all synchronized and all precise enough, you might be able to detect those fluctuations as the Earth moves through a dark matter field. It's a completely different way of thinking about what a clock is for. Similarly, there are proposals to use networks of optical clocks for gravitational wave detection. We already have LIGO and Virgo, those magnificent laser interferometers that detected gravitational waves for the first time in 2015. But optical clock networks could potentially detect gravitational waves at different frequencies, very low frequencies that LIGO can't access. A gravitational wave passing through a network of clocks would cause the clocks to tick at slightly different rates relative to each other, and with sufficient precision, you could pick that signal out. This is the pattern that keeps repeating throughout the history of timekeeping, and it's so consistent that it almost feels like a law of nature in itself. You build a better clock. You think you're solving a practical problem, tracking the seasons, finding your longitude, synchronizing your trains. But the clock turns out to be more precise than you expected, and that extra precision reveals something you weren't looking for, something about the Earth or about gravity or about the nature of matter. And then that discovery reframes your understanding, which leads to new questions, which demand even better clocks. It's a spiral, really. And right now, we're on a part of that spiral where the questions are getting very deep indeed. Because if time is emergent, if it's not fundamental, but arises from something more basic, then what does it even mean to measure it? What is a clock measuring when the thing it's supposed to be measuring might not exist at the bottom level of reality? There's a beautiful thought experiment that the physicist John Wheeler used to think about. Wheeler, who coined the term black hole and was one of the great figures of 20th century physics, imagined what he called it from bit. The idea that the physical world, at its most fundamental level, might be made of information rather than matter or energy. In this view, time might be something like a story that the universe tells about itself, a way of organizing the relationships between quantum events into a narrative that makes sense to beings like us, beings who exist at a particular scale and experience the world in a particular way. Time, in this picture, isn't a river that flows. It's more like a book. The pages are all there simultaneously, but we experience them one at a time. Now, whether that's right or not, and honestly, nobody knows. It's the kind of question that our clocks are now precise enough to start poking at. And that brings us to something that might seem like a detour, but is actually deeply connected to everything we've been talking about. The way that timekeeping has shaped not just science and navigation and technology, but our everyday experience of being alive. Because there's another side to this story, a more human side, about what it means to live in a world where time is measured with such extraordinary precision, and what we've lost and gained along the way. Think about this. For most of human history, and we're talking tens of thousands of years, people lived by what you might call body time. You woke up when the light came through whatever opening served as your window. You ate when you were hungry. You worked while the sun was up and you stopped when it got dark. The seasons told you when to plant and when to harvest, and the moon told you roughly where you were in the month. And beyond that, time was this soft, stretchy, deeply personal thing. Nobody was late for anything, because there was no minute hand to be late against. Nobody felt rushed, at least not in the way we mean it now, because the whole concept of minutes slipping away from you, that's an invention. That's something we built. And it happened gradually, so gradually, that nobody really noticed the world changing around them. The first mechanical clocks in those medieval church towers, the ones we talked about way back at the beginning of this story, they didn't even have minute hands. They just had hour hands, and honestly, they weren't even very good at tracking hours. They'd drift by 15, 20 minutes a day, and nobody cared because the resolution of daily life was coarse enough that it didn't matter. You showed up at the market sometime in the morning. You went to church when the bell rang, and if the bell was a bit early or a bit late compared to the sun, well, who would know? Who would check? But then Huygens built his pendulum clock, and suddenly you could track minutes reliably. And then Harrison built his marine chronometers, and suddenly you could track seconds. And then the railroads came and demanded that everyone in a country agree on what time it was. And then the telegraph made that synchronization possible across oceans. And then quartz oscillators gave us clocks cheap enough to put in every home, every office, every pocket. And now we carry atomic-grade timekeeping in our phones, synced to GPS satellites that are themselves corrected for the curvature of space-time. You can pull a device out of your pocket right now that knows what time it is to within about 100 nanoseconds, 100 billionths of a second. And here's the thing. You use it to make sure you're not 3 minutes late to a meeting. There's something almost absurd about that, isn't there? We built clocks that can detect the difference in the flow of time between your head and your feet, and we use them to set alarms so we don't oversleep. We have instruments that could theoretically detect dark matter passing through the Earth, and we sync them to the same time standard that tells the microwave when to beep. The most profound physics humanity has ever done, and the most mundane moments of daily life, they're connected by this single thread of timekeeping. That's remarkable, but the human cost of all this precision is worth sitting with for a moment. The historian E.P. Thompson wrote a famous essay in 1967, the same year, actually, that the second was redefined using cesium, called Time, Work, Discipline, and Industrial Capitalism. And Thompson traced something really interesting. He showed how, as clocks became more accurate and more widespread in the 17th and 18th centuries, the entire relationship between people and their labor changed. Before reliable clocks, work was task-oriented. You didn't work for 8 hours. You worked until the field was plowed, or the bread was baked, or the net was mended. The task itself defined the time. But once factory owners had clocks, good clocks, clocks with minute hands, they could start buying something new. Not your labor in the sense of what you produced, but your time itself. You sold hours now, minutes, and if you weren't producing during those minutes, you were stealing from the person who'd bought them. That's a profound shift. It changes what time feels like from the inside. Time stops being something you inhabit and starts being something you spend. And Thompson showed that this wasn't natural, wasn't inevitable. It was engineered, quite literally. Factory owners in the English Midlands in the late 1700s would sometimes set the factory clock forward in the morning to get workers in earlier, then set it back in the evening to keep them later. Workers figured this out, of course, and started carrying their own pocket watches, which were becoming affordable thanks to mass production, specifically to check the boss's clock. Time became contested territory. The clock became a battleground, and that tension never really went away. It just got more sophisticated. When the railroads imposed standard time in the 1880s, there were people who genuinely resisted. Not because they didn't understand the practical necessity, they could see why trains needed a shared schedule, but because they felt something was being taken from them. Their local noon, the noon that was real, the noon when the sun was actually highest in their sky, was being replaced by a noon that was administratively convenient. And they weren't wrong to feel that loss. Something real was lost. The connection between the time on the clock and the time in the sky, the time in your body, the time in the world around you. That connection was severed, and it's never been restored. Now, you might say, well, that's progress. That's the price of coordination in a complex society, and you'd be right. The benefits are enormous. Modern life, air travel, global markets, the internet, GPS, everything, depends on shared, precise time. You can't run a civilization on sundials. But it's worth noticing what happened, worth sitting with the fact that the most intimate human experience, the felt passage of time, was reshaped by engineering decisions made for practical reasons by people who were mostly thinking about train schedules and factory shifts and naval navigation. And here's where it connects back to those deep questions about the nature of time itself. Because one of the things that modern physics tells us, and our clocks are now good enough to confirm this experimentally, is that there is no single universal now. Einstein showed this more than a century ago. Two events that are simultaneous for one observer are not simultaneous for another observer moving at a different velocity. Time is local. Time is personal. Your time and my time are not the same time. Not exactly. Not if we're moving differently, or sitting at different heights in a gravitational field. And yet we've built an entire civilization on the assumption that time is shared, that when I say 3 o'clock, you and I mean the same thing. That's a fiction, a magnificently useful fiction, an engineering triumph of a fiction, but a fiction nonetheless. UTC, Coordinated Universal Time, the time standard that the whole world runs on, is assembled from a weighted average of about 450 atomic clocks in over 80 laboratories around the world. The Bureau International des Poids et Mesures in Sèvres, France, just outside Paris, collects data from all these clocks, compares them, weights them by quality and stability, and produces a single time scale that is published about a month after the fact. The time on your phone right now is an approximation of a prediction of a retroactively computed average of hundreds of clocks that don't quite agree with each other. And it works beautifully. It works so well that you never think about it. But it's worth thinking about, at least tonight, because it captures something essential about the whole story we've been telling. From the very beginning. From those first humans watching the sun track across the sky. From the Egyptians dividing daylight into 12 parts. From the anonymous genius who realized that dripping water could mark the passage of hours in the dark. Timekeeping has always been about imposing order on something that doesn't inherently have the kind of order we want it to have. The universe doesn't come with a clock. It comes with processes, oscillations, rotations, vibrations, decays, and we choose which processes to call our clock. We chose the sun, then the pendulum, then the quartz crystal, then the cesium atom, and soon, probably, the strontium atom or the aluminum ion. Each choice gave us more precision, and each new level of precision revealed something we didn't expect about the nature of time itself. The Earth's rotation turned out to be irregular, and we only discovered that because our quartz clocks were better than the Earth. The second turned out to be definable in terms of atomic transitions, and we only realized how powerful that was because Essen and Perry built a cesium clock and showed that atoms are more reliable than anything astronomical. Gravity turned out to affect the flow of time, and we only confirmed that with the precision that modern life demands because the GPS system wouldn't work without relativistic corrections. And now, optical clocks are precise enough to detect the gravitational influence of a small mass in a laboratory, which means we're using time to measure gravity, which means we're using the thing that gravity affects to measure gravity itself. There's a beautiful circularity there, a kind of loop that would have delighted someone like Wheeler. And what comes next? Well, if the pattern holds, and there's every reason to think it will, the next generation of clocks will reveal something new. Maybe they'll detect dark matter. Maybe they'll find tiny violations of Einstein's equivalence principle that point toward a theory of quantum gravity. Maybe they'll discover that time really is emergent, that at the Planck scale there's something more fundamental, and that what we experience as the flow of time is a macroscopic approximation of something we don't have words for yet. Yunye's strontium clocks at JILA, the optical lattice clocks being built in Paris and Tokyo and Braunschweig, the trapped ion clocks at NIST and the National Physical Laboratory. These instruments are right at the edge of where known physics meets unknown physics. They're the telescopes of the 21st century, except instead of looking outward, they're looking inward, into the fabric of reality itself. But you know what? You don't need a strontium lattice clock to experience the mystery of time. You're experiencing it right now. Right now, as you lie there, your body is doing something that no clock can fully capture. Your heart is beating at its own rhythm, not quite regular, subtly responsive to your breathing, your thoughts, your level of relaxation. Your brain is shifting through patterns of activity that will carry you from waking into sleep, through stages that cycle roughly every 90 minutes, but never quite the same way twice. Your cells are repairing themselves according to circadian rhythms set by ancient evolutionary clocks that predate humanity by hundreds of millions of years. You are a collection of biological oscillators, all ticking at different rates, all entrained to each other and to the 24-hour cycle of light and dark that has governed life on Earth since long before anything with eyes existed to see the sun. And that's maybe the deepest thing about time, that it's not one thing. It's not just what clocks measure. It's not just what physicists theorize about. It's also what you feel, lying here in the dark, as your thoughts slow down and the day recedes and the boundary between waking and sleeping gets soft and blurry. The Egyptians knew that feeling. The monks who listened for the church bell in the middle of the night knew it. Harrison, working alone in his workshop in Barrow upon Humber, filing brass and cutting gears by candlelight, he knew it too. Every person who has ever lain awake and felt the night stretching out around them has touched the same mystery. Time is the thing we understand best and least. We can measure it to 18 decimal places. We can correct for the curvature of space-time. We can define it in terms of 9 billion oscillations of a cesium atom. And we still don't know what it is. We don't know why it flows in one direction. We don't know whether it's fundamental or emergent. We don't know if the question even makes sense. But here's what we do know. We know that right now, in this moment, you're here. The day is done. The clocks are still ticking. The cesium clocks in their temperature-controlled vaults, the GPS satellites in their orbits 20,000 kilometers overhead, the quartz crystal in your phone on the nightstand. But you don't need to keep time anymore tonight. You can let it go. You can let the seconds pass without counting them, the way people did for thousands of years before anyone thought to build a clock. You can just rest and let time do what it does, which is carry you gently forward, one quiet moment at a time, into sleep.